Okay, so now that you have this geometry in mind, let's ask a very simple question. Okay, what is the primal problem? What is the primal problem and referring to the YZ plane? So what would you say? You have the YZ graph in front of you, right? So how would you state the primal problem? And you can refer to this guy. In the primal problem, what were we trying to do? Minimize f such that c greater than equal to 0. That was the primal problem. Minimize f such that c greater than equal to 0. Now, can we express this in the YZ language? Minimize z such that y greater than equal to 0. Z, there is no z is negative. Z is, I want to make z as low as possible. Don't confuse the objective function and the constraint. So forget this mapping. Even if we had not done this mapping, what is the primal problem in the YZ coordinate? Give me as low a possible value of z, which is f, such that y was greater than equal to 0. That everyone will agree. Now that we have, so let's just write that down over here. So the primal problem is minimize z such that y greater than equal to 0. So in this YZ plane, what is this? Can we immediately see the solution? What is it? It's where this pink curve is cutting the z point, right? It's basically this point over here, the orange point, because this is the smallest value of z that I can have while y is greater than equal to 0, while I am in the right half plane, right. So in this YZ plane, I have got the solution again graphically. Okay, so again the primal problem was simple, just right. So don't think that x coordinate axis is primal problem, YZ is dual problem. That's not the thing. We are going to do this transformation and look at the primal and dual problem both in the YZ system. Okay, so can be easily seen. Okay, and for ease of reference, this pink curve I am going to call G, capital G. Okay. Now, maybe I don't have enough space, so I'll go to the next slide. So the next question is, okay, let's just draw this again. Okay. So for solving the dual problem, what was the first thing that let's write down our favorite Lagrangian, because this is going to be very key. F of x minus lambda c of x. Okay. Right. Now f was mapped to what? Y or z? Z. Right. So this was equal to z minus lambda y. Okay. So just for shorthand notation, this L of x comma lambda, I'm just going to give it a shorthand notation. Let's call it alpha. Okay. And this was my y, this is my z. So this equation which I have got, which is the equation of the Lagrangian, what does it say? It says that z is equal to lambda y plus alpha, right. This is like y is equal to mx plus c, right? I know the slope and I know the intercept. Okay, so now let's look at step 1 of our Lagrangian formula. So I need to do what first? Write the Lagrangian dual, right? So q of lambda was minimize over what? X, right? And x belonging to what? Obviously the feasible region, right? So let's say this is the feasible region and the Lagrangian of x comma lambda. Okay. Now let's write this in our new language. So what is a Lagrangian? It is z minus lambda y. Z minus lambda y like 2. Z minus lambda y. Now that I am in the yz space, I need to translate x belonging to feasible set into yz belonging to feasible set. Obviously, because y and z are not free to be anywhere. So I can say this, we had already marked this region as G. So I will just say that yz belonging to G. Just a convenient way to denote this whole thing. Okay. Actually, let's correct that. It should not be yz belonging to G. It should simply be y greater than equal to 0. That was the feasible range, right? So let's. But there is a relation between y and z, right? So that's okay. So let's leave that here, because y and z are not free to be any 2 points on this. Y and z are constrained to be by that quadratic relation. So that quadratic relation is what I am calling G. So y and z are this, and we can say that y is greater than equal to 0. That captures the constraint, right? So this is a sort of a clumsy way of saying that respect the mapping and stay feasible. You are not free to choose y and z as you wish. They are related by this parabola. Okay, so now z minus lambda y is what I want to reduce. So before talking about what I want to reduce, why don't we try to plot what does this look like? This is a line with slope what? Slope is lambda, intercept is alpha, right? So what would it look like? I have to be, let us say, on this G thing. Lambda is fixed. In the definition of Q, lambda is fixed. You give me some lambda, for that I will give you a Q. Okay. So if I just wanted to sketch different lines of this, they would be straight lines with slope lambda, intercept alpha, right? So they would basically look something like this, right? So this is z is equal to lambda y plus alpha, and when I do this, what is the value of alpha? This much, right? This is my value of alpha, right? All of these guys go. Okay. Now I am saying that I want y and z should belong to this parabola, right? So is there a further constraint on this line? It should touch this, it should be tangent. I want to be on this curve, for example, right? So not necessarily, I mean, I could be anywhere inside this cup region, that's okay. So these are all, so let's go step by step. These are all the possible straight lines that respect this equation, right? Now what do I want to generate the Lagrangian dual function? I want to minimize this guy, z minus lambda y. This z minus lambda y is what? Is basically alpha. So what am I saying now graphically? Keep reducing it, right? That's how I'm going to reduce my intercept. Keep bringing this line as far down as possible, but I can't do it forever and ever because yz should belong to G. So what is the smallest thing I could do? Tangent, right? So I'm going to get something like okay. My drawing is terrible, but if I start erasing this, everything gets erased. Okay, let's assume that this is the tangent point. Okay, so my pathetic drawing is okay, right? So these are all different lines, all same slope. Okay, and this is the minimum intercept, right? So this alpha over here is as low as I could get, because if I try to reduce this intercept any further, what would happen? I would leave this pink region. I would basically fall out. So that's my problem. Okay, so this has given me what has it given me? It has given me a geometric intuition of what this Lagrangian dual function is. Like, give me lambda, I'm going to keep reducing this until I just leave the region, so that tangent place is where I live. Okay, so alright, that's good. That was step 1. Step 2. What is step 2? Having got the Lagrangian dual, what did I want to do? Maximize it. Right. So step 2 was basically max over lambda, q of lambda, such that lambda greater than equal to 0. Okay. So in step 1, basically, okay, so let's again plot it. This is my G region. Okay. For different values of lambda, what is this equation z is equal to lambda y plus alpha? What is it representing? Basically, lambda is controlling the slope. So here in this optimization problem, maximizing over lambda, what am I varying? I am varying the slope, right? So they are basically all are different tangent lines. So I could have something like this, I could have something like this, and so on, right? These are all different tangent lines, which are, what are they corresponding to? They are corresponding to different lambda. As I vary lambda, right? And because this q is coming from step 1, it is forcing, that is what is forcing them to be tangent. Otherwise, they could have gone inside also, right? So the tangent line is coming from step 1. Step 2 is varying the slope of the tangent. That's what I am doing. Is it clear? Okay. So if I mark the tangent points over here, I could have a tangent point over here. Okay, so I could have a tangent point over here. I could have a tangent point over here. I mean, there are infinite tangent points. I'm going to call this T1, T2, T3. Just as an example, I've taken 3 tangent points. Okay. So let's see what this says. So I want to maximize over lambda. I'm going to put a special symbol now on z, because these z and y are coming from the previous step, they are optimal in some sense. So this is they are not any y and z, they are special y and z, y plus z plus, which have come from the previous step. Okay. T3 is not a feasible, they are just examples of different tangent points, right? Now, okay, this is what the step 2 says. Again, let's interpret this in words. This whole problem, maximize z plus minus lambda y plus. What is z plus minus lambda y plus? It's again alpha plus, which is what? Intercept. Right? So this is both, alpha is always the intercept. Okay, so now what am I saying? Step 2, I am saying maximize the intercept. Of course, while staying feasible and all of that, right? So of these 3 lines which I have drawn, which have tangent points T1, T2 and T3, I want to maximize the intercept. So for example, for this T1 guy, what is the intercept? This guy, right? This is alpha 1. T3 anyway is not feasible because that point is in y less than 0. What about T2? T2 is on the z axis, so it is feasible. And of all possible tangent lines, which one do you think will have the highest value of intercept? Not mod alpha, alpha. Who has it? T2, right? For the line where T2 is the tangent, that's the thing where the intercept is maximum. If I go any further to the right, what happens? The intercept becomes less, becomes 0. By the time I come to T1, it has actually become negative. Right? So, this happens at T2. Okay. Okay. Is step 1 clear? Step 1 is clear, is that give me the least possible value of intercept and I am staying on the feasible part, right. Now in step 2 what am I doing? I want to maximize the intercept because z plus minus lambda y plus is the intercept of some line. What is my optimization variable in this step 2? What am I allowed to vary? Lambda. Lambda is in my hand. Right. So, you can quickly alternate between step 1 and step 2. Q, you have to give me a lambda. If you give me a lambda, I will give you a Q. How will I give you a Q? I will basically find out a tangent line to G. That is my Q, right. Now that you have given me a Q, that means Q is basically the family of all tangents to this guy. Now in step 2 I am saying, hey, of all of these guys, give me that tangent line which is maximizing the intercept. And that maximization of intercept you can see graphically is happening at T2. If I go any further to the left, the tangent jumps into infeasible region. If I go any further to the right, the intercept value reduces. So the best intercept that I am getting, because this step is a maximization step, is coming from this particular guy T2, right. So you would then say T2 is the solution to the dual problem. Okay. So in fact, the solution to the primal problem and the solution to the dual problem. Remember in this case it was T2. In the previous case we saw that the true solution to the primal problem was the same point where this parabola is cutting the z-axis. Yeah.
So parabola will cut the z-axis means it's y equal to 0.
Yeah.
So z which we are getting is 8 by 5.
Okay.
But the question answer we got was 4 by 5.
The y equal to 0, where are you substituting? Here. Yeah.
So we will get 2 into 2 square by 5 which is 8 by 5. But like without using this duality, without using this y-z translation and we just originally solved using t,
correct,
we got 4 by 5 as the answer.
we got 4 by 5 as the answer. Have we made a mistake somewhere in the algebra?
So is it true that all parabolas will lie above this?
Yeah, I mean you have to
growth wise 2a square by 5 will grow bigger than a
right.
For like I can still find some values of a for which 2a square by 5 might be less than a.
Oh, okay, I see the problem. No, so okay, so there's a little bit of confusion. This a equal to 0 line which I took is just to show, it's the simplest parameter of a to put inside for you to see it's a parabola. Okay. This G region, because this is not a very easy thing to sketch, right? I'm not actually marking the value at which this G region is cutting the Z axis. It is not for a equal to 0. Okay, you have to do this carefully. The sketching has to be done carefully. The lowermost boundary of this is need not be for a equal to 0. In fact, what you're saying proves that it is not for a equal to 0. So you do this for different values of a, you'll come up with some region G which looks like this parabolic region. Okay, so this cutting point is, yeah, you're absolutely right. This cutting point need not be for a equal to 0.
Maybe like you can say for given y, this a gives the least z, something like that.
I mean, not necessarily. Let's just imagine that this is some region, pink region, okay? And so that's why I'm not putting any numbers down on this orange point. At some point, a equal to 0 was just chosen so that you can immediately see it's a parabola. That's all.
That region would also remain convex because our original parabolas
Yes,
are all convex.
they're all convex. Yeah, that's a good point. Okay. So in this case, the primal solution, just one moment, is equal to the dual solution. Yes. No. Choice of A is not related to choice of lambda in any way. What is the motivation that I had in choosing x2 equal to A? Can anyone try to read my mind? It's to basically do the mapping. If I take different values of A from minus infinity to infinity, I will, if I plot it on the yz plane, I will see what is the entire x1, x2 region mapping to. So it's a coordinate transformation, you can think of it. And that coordinate transformation gives me this pink region. Yes. Seems like magic. There are so many such transformations. You can map a half plane into a circle. So if you take a course on complex analysis, you have all these kinds of mappings that happen. Nothing very surprising about it. Z transform. Yeah. Okay, so we have this situation here where the primal solution is equal to the dual solution, and it's because you saw the problem and the constraint were convex, right? Question. We choose a tangent to the pink region of slope lambda because lambda is fixed. Yeah. So wait, before you go to step 2, keep in mind step 1 is not one tangent. Step 1 is a family of tangents for different values of lambda. So it's like I have a database of all of these possible different tangents. Now in step 2, what I'm going to do is choose the tangent which gives me the highest intercept, right? That's a convenient way of thinking about it. Okay, so when these guys are equal, this is called, as I already mentioned, strong duality. Okay. So there is just one small update that I want to give to the definition of the Lagrangian dual, because it did not come in the problem, but in general a small update on sort of more general of Q. Okay. It can happen that for some lambda, for some lambda, it can happen that Q of lambda goes to minus infinity. It can happen. As we saw, this was a concave function. So there could be some lambda for this, for which this goes to minus infinity. So the domain of Q is defined like this: lambda such that Q of lambda is basically not blowing up. Okay. So this just keep this in mind. This is a small technical point, but when you do your dual problem, when you are formulating your Lagrangian dual function Q of lambda, there we said okay, lambda could be anything, but you have to keep in mind that those lambdas which lead to Q blowing up are not allowed in the domain of Q. This is one small point to keep in mind. Okay. So I
Basically, like we're only allowed values of lambda such that the Hessian is positive. Like Hessian of the Q with respect to lambda is positive.
nothing to do with positive definite over here, right? In fact, Q is concave, so it's negative definite. Negative definite. So a negative definite function can also blow up, right? Right? The parabola going down at some value of lambda, it will go to minus infinity. So what this is saying is that the domain of Q should be restricted to the region where it does not blow up, just so that it makes sense to talk about Q. That's all. As I said, this is like a minor technicality. You need not worry too much about it. Okay. Okay, so I think this is a good place to stop. There are certain properties of Q which are very useful and powerful. We'll look at it in the next class. Maybe I'll just state the properties, I won't prove it, okay, because Karthik had asked the question. So, two results about Q or about the dual problem, which we will prove the next time, okay. Q is concave. The second is this D, which is the domain of Q, is convex. And here is the sort of rabbit out of the hat. For absolutely any f comma c, any f comma c, that means f could be non-convex, right. So this is why this the dual problem ends up being very special, because you can throw whatever problem you want in the primal sense. When I make the dual problem corresponding to it, I always get a concave problem, right. So if I always know that a problem is concave, isn't it, it's like it's just the negative of a convex problem, right. So that's why in general solving the dual problem is easier, because it's you're dealing with a, if I know how to deal with a convex problem, I know how to deal with a concave problem, right. It's just turn my paper upside down basically, right. So that's why this is one of the powerful motivations behind research on the dual problem. It gives me a concave problem, and the domain of this function is convex. And we have seen all the proofs that we have used about, various things have used convex sets everywhere. So this gives us a very strong theoretical basis to think of convergence proof and all. But the flip side is that if f is, if for any f or c, so if f is non-convex, you can solve the dual problem. It does not solve your primal problem, because there can be a duality gap. The solution that you get to the dual problem and the solution of the primal problem, they need not be the same, there can be a gap. So you may get a solution, but there may be a better solution of the primal problem that is missing from here. Which boundary? Yeah. But the dual problem is always concave. I mean, there is a proof. We will study the proof in the next class. Not very tough. Okay.